I can do it either way. I can do it master, or we can keep them off and you can turn them to green when you want to. These are really nice.
And I also have the description next to it. Oh, for the conference, if you wanted to.
Oh, Serena. Can you guys hear me? Hello?
Yes, we can hear you, Alicia.
Great.
Padhraic in Irvine.
So I just wanted to say hello to everybody. We are launching our fall series of the webinars. Great to have you all here. Our speaker today is Padhraic Smyth from the Department of Computer Science and Statistics at the University of California, Irvine. He is a member of the Irvine CSAFE team and will talk to us about methods for analyzing event time data, I should say. Do we have any announcements? No. So at this moment, I think we have no more announcements. So Padhraic, just take it away.
Alicia, this is Barbara Hervey joining in too. Just wanted to let you know.
Oh, Barbara, welcome. Good to hear you.
Thank you.
And we have our friends from Israel. This is great. All right, go for it.
Hello, this is Padhraic from UC Irvine. We have about 8 or 10 of us here at UC Irvine watching on the screen. So today I'm going to be talking about work in the area of digital forensics under CSAFE. And this is joint work with Chris Galbraith, a PhD student, and Hal Stern, who is the UCI PI on this CSAFE project. So, hold on. Hang on while I get the hang of this. All right. Okay. So what I'm going to do is give some background on digital forensics in general, some broad concepts, and then we'll focus in on user-generated event data. And we'll talk about how we can formulate specific questions about this type of data, And in particular, we'll talk about event streams and if we can develop techniques to determine if they're from the same source or different sources. And so we'll go through some ideas of statistical methodology we can use to try to answer these questions, and then wrap up with some current work and future directions. I should say that there's a fair number of these slides that a fair number of people in the audience will have seen already. So apologies in advance to some of you who've seen this. Some of you have seen this twice, or some maybe even 3 or 4 times. So, but there's also some new stuff in here that I think nobody has seen, including my collaborators, Chris and Hal. So hopefully there's something for everybody here. So a question that's asked often is, what is digital forensics? What is digital evidence? I'm not going to answer that. We could spend an entire hour or more, and we have done in the past, going around in circles trying to answer this. But I took a definition just to give you an idea. This is from a National Academy study about 10 years ago. Analysis of digital evidence deals with gathering, processing, interpreting digital evidence such as electronic documents, phone numbers and call logs, records of a device's location, emails, photographs. And then they go on to say, in addition to traditional desktop and laptop computers, we can also have cell phones, GPS devices, digital cameras, and so on and so forth. So this sort of by example gives you a sense of what digital evidence consists of and digital forensics. And of course, obviously in the context of criminal investigation, since criminals use all these devices. And it's become increasingly important for forensics in general to take account of digital evidence. And this is just a sort of slide indicating that in the US population, this is from Pew Research, more and more people are using smartphones, using social media and tablets and so forth. So criminals are no different, or people who are involved in crimes. They're also going to have computers and cell phones, and it's important to be able to analyze the relevant evidence. As an example, this is a slide from Simpson Garfinkel. If you just look at cell phones, there's quite a lot of technology that has to be developed just to get the data off cell phones. The operating systems change frequently, as we know. There's different types of operating systems. Data may be encrypted, it may be stored locally or in the cloud. There's all kinds of different applications, tens of thousands, hundreds of thousands of applications that could be on the cell phone. So developing the software to get relevant data off a device like a cell phone is a large component of digital forensics work. And this is just some papers that were presented at the Digital Forensics Symposium in August that was held in August in Austin, where my student Chris attended. And this is very typical. This is just 6 papers out of maybe 40 that were presented. These are very focused on kind of details of getting data off mobile devices, memory issues, and so forth. So a lot of the existing work in digital forensics is focused on more on the computer science side of how do you extract data, how do you deal with encryption, file formats, and so forth. The bigger picture, of course, is that there's sort of the general background. This is also a slide from Simpson Garfinkel. You want to collect the evidence off the phones, which is what we've been just talking about. You want to preserve that data. And what we're interested in CSAFE in particular is sort of the, what I've highlighted here, the analysis component of once you've extracted the data, how are you going to analyze it? And in our CSAFE project, that's what we're focusing on. So we're not looking at techniques for getting data off devices. We're assuming that that's a fairly straightforward process, or we have tools to do that. We want to know or have techniques to deal with the data once we've extracted it. And this is a slide I took from Mark Pollitt, who did a nice CSAFE-wide presentation a few months ago. And he was putting in the broad context, again, of digital forensics, what kinds of contexts exist and what kind of questions a forensic examiner might want to ask. And so in terms of context, you have the person, the user, you have the computer, you have the application that's running, the operating system, the file system, all these different aspects that can complicate the analysis in a certain sense or bring different perspectives to it. And then he tried to categorize high-level questions you might ask about who, what, when, and then more specifically forensic questions that could be asked. So in the context of Mark's slide, in today's presentation, I was looking at this and saying, okay, the work we're doing is focused on users. It's focused, as you will see, on the who and the when. We're looking at timestamps in particular, and we're answering questions about association. 2 different event time series, are they associated or not? So talking about user-generated event data, and I use the term user-generated because on any device, there's a lot of logs of event data, and a large part of that is often system-generated data by the software, by the operating system. It's updating things and so forth. We're interested in the logs, the events that are recorded that reflect human behavior, activity of the person who is logged into the device. And so this might be coming, again, from particular devices, cell phones and so forth, or from the cloud. And when you start looking at this, there's actually a lot of different types of, we leave digital traces all over the place. And of course, companies like Google and Amazon and Facebook are very well aware of this, but on your own device, if you go looking, you'll find browser requests, web searches, email activity, if it's a cell phone, text messaging, social media activity, GPS locations, if GPS is turned on, file access, the times that you access files, network activity when you got on a wireless network, perhaps even movement activity on a phone. And a lot of this data, again, I think people are sometimes surprised to find this out, is routinely logged, and either on the device itself or more frequently now in the cloud. So, you know, the type of data natively, locally on the device that's easy to find is your browser history, things like cookie files. And in the cloud, you know, all of your email history, for example, for Gmail, your search history for browsers like Google Chrome, and on the right here, this is kind of the format that it might come in, where there's timestamps and there's the text of the query and so forth. File editing, if you're using, you know, cloud-based document editing, and your social media activity. If you go to Facebook, if you're on Facebook, for example, you can download a lot of information about your entire history of activities on Facebook and when you posted and what you posted and so forth. Now, using this data for forensic purposes, there are some caveats that I'm going to pretty much largely ignore. You know, a user might purposely delete this data, might obfuscate the data. To get access to this data, even on a device, you may need a password of the account, and in the cloud, again, you'll have to have some way to access that data. I'm going to assume that that's not an issue. It will be sometimes an issue, but we'll assume that we've gotten past that stage in looking at a device. So there's already work out there in looking at this type of data. And this is just an example of a toolkit, Autopsy, and some other tools that go with it that take multiple different types of log data and try to visualize it and analyze it in various ways. So for example, you can look at timelines of user activity. This might be file editing or file access maybe over a long period of time. And so I'd say a lot of the existing work to date has been on visualization exploration rather than statistical analysis. So in terms of what this data looks like once we take it out, it's often in kind of large text files or things like JSON files and so forth. We can think of the primitives here as representations of events, where we have the individual ID, the person, the name of the account, if you like. We have the timestamp, usually down to seconds. There may be some issues with that in terms of where you are in the world, what time zone is being used, how accurate is the time on the device. I won't talk about that today, but that can be important. The action type. So is this is it a search query? Is it a page request in web browsing? Is it an email sent? So from a slightly more abstract point of view, we can think of categorical types of actions, different types of actions that tell us something different about users, for example. And then we'll often have metadata as well. And the simplest example might be text content. So if it's a search query, what is the text of the search query? If it's an email, what is the text of the email? Could be also the list of the recipients. Again, there's a lot of information in there. In today's talk, I'm not going to talk about that. I'm going to primarily focus on basically the timestamps and essentially two action types. So we'll see that as we go forward. So what does this data look like? This is from an individual. In fact, it happens to be me. And you can look at your own data quite easily. This is from the Google Chrome browser. So the x-axis is time going back about 2 years when this data was gathered. And the y-axis is 24 hours in the day. So every vertical line here is a different day. And what you can see is that there's quite a bit of structure in this type of data. Generally, if this is midnight at the bottom on the y-axis, I'm not searching the web in the middle of the night, so I get some sleep, and then I start working on the web, typically around 9 a.m., looks like, sometimes a little earlier, and it goes on until the evening. And so, again, this is kind of this regularity in this timestamp data is you see this pretty often. Here's again same individual, i.e., me, from my desktop computer, and here's a little bit more information. There's for example, so the same type of plot. The vertical lines are 24-hour periods. We see, for example, a big gap here, and this corresponded to when I was on travel and I wasn't physically close to the computer. So that's the type of information where we can gather from these types of event logs. This starts to get interesting when we superpose two different event types here. So what I've done here is I've taken the data we had previously, and that's plotted in blue. That was browsing on my desktop, URL requests, page requests. And I've superimposed page requests that were coming off my laptop. And you'll see that they're, to a large extent, mutually exclusive, that the laptop requests, I'm using the laptop generally when I'm not using the desktop. And in fact, there's other sort of interesting subtleties to this data. If you look at it, you see that I tend to use the laptop maybe first thing in the morning sometimes, and also later in the evening when I'm not at my office. And also that time period previously when I wasn't using my desktop, I had my laptop with me and I was using my laptop. So a question that we're now starting to get to questions that we might be able to answer using statistical techniques. Can we quantify the extent that in an example like this, that these two data streams, the red and the blue, were generated by a single individual, that they're consistent with coming from a single individual? Maybe more precisely, can we quantify that they're dependent in some sense? There is some notion of dependence between the red and the blue. We can see that appears to be the case. We know it's the case in this situation, but can we quantify it? So the type of data we're going to look at is, it's going to look like this. This is going to be from a study of students that was done at UC Irvine. And here are three different pairs of event streams. Each one has red and blue. The x-axis here is time. It corresponds effectively to time of day, actually. So again, the 24-hour period was on the y-axis before, now it's on the x-axis. We're going from 0 to after midnight, so professors are usually asleep here, but students continue into the late night, early hours of the morning. And I'll explain what the blue and the red are a little bit later on, but the first box is, well, let me just back up for a second. We have three pairs of event streams here, and the question that we would like to be able to answer is, how likely is it that these are coming from the same individual in each case? And from this data, you can't really tell. It's difficult. The first pair of red and blue are very dense. The second pair, quite sparse. The third pair, hard to say. So it turns out that the first and second pairs are actually coming from the same individual. This was the same individual doing two different types of actions. And the third one is two different individuals, where we've taken red event from one individual and blue from different individuals. If we back out in time to a whole week of data, which is the full data set that we have, it's much more clear. For the first individual, you can now see the correlation quite clearly between blue and red. This doesn't look like it's happening by chance. The second individual, it is the same individual. And if you look locally in time, you can see that the red is embedded within the blue, but it's not nearly as clear that they're actually dependent, but it is actually the same individual. And the third one, it turns out the blue is coming from one student and the red from a different student. They're two different individuals with these blue and red actions. So what is this data that I just described? It's data from a colleague here at UC Irvine from a National Science Foundation funded study where there's let's say order of 100 students with anonymized identities. We have 1 week worth of data, which you just saw for some of the students. And it's in this form that we want, which is basically the ID of the student, the timestamp, the event type, the metadata. There's actually a few different types of actions in here. There's URL requests, there's opening apps, there's sending text messages. We're just going to focus on the URL, page requests, and browsing. And the data was taken off devices. The students loaded software onto their devices for a week on it was Android phones and Windows laptops. So it was actual data coming off actual devices. We're in the process of trying to get more data, a larger data set at UCI. And I'll mention towards the end, there are other data sets, some publicly available, that we may be able to use in this research that we're looking at using. If you take those students, this is about 50 of the 128 total students. This is a very dense plot that Chris generated. So on the x-axis, we have time. On the y-axis, we have different students. So let me explain what's going on here. If we take the very top student, ID 122, there's going to be black dots and red dots. So the black dots are Facebook activities in the browser, where we get a timestamp that they did a page request within Facebook, and the red dots are non-Facebook activities within the browser. And the idea here is that we've separated out two event streams, the Facebook and the non-Facebook, and for these students, we expect that there should be correlation. It would be surprising if there wasn't. We'd expect that the Facebook typically will happen embedded within other non-Facebook activities in the browser. And indeed, you can see that with many of the students. If you look vertically or go down through the different students, there's a lot of overlap. At the same time, it's not entirely clear how you quantify this. It's not obvious. For some of the students, they have relatively little data, and it's not obvious that you can tell that the black dots and the red dots line up. Another way to think about this is if we jumbled the horizontal lines with the different traces of events, instead of pairing them up with the correct students, just had them randomly assigned to different students, it would probably be quite difficult to line up which black dots go with which red dots, which event streams. So I guess the point I want to make here is that even though the Facebook, non-Facebook dichotomy is a little artificial, it's actually a non-trivial data set to figure out the appropriate level of association between the two event streams. And it's also quite useful. It is real data. The other thing you'll notice as well is that there's a kind of a background rate that even the students go to sleep in the middle of the night. There's a pattern, a time of day pattern that influences all of the events, and that's actually important to take that into account. So the challenges with analyzing this type of event data, what kind of models, if you want to have a parametric approach, some kind of Poisson model, for example, it's not obvious what appropriate modeling assumptions are. This is partly because you have these non-stationary background rates, time of day effects that I talked about. You also have burstiness, very typical in this type of data, where somebody sits down at a computer for a while, and then they get up and go away and do something else. So you'll tend to get bursts of events that are non-homogeneous, superposed on top of the background time of day general background rate. There's also high within individual variability from day to day. So students, or ourselves, we don't follow precise patterns. And I'd contrast this maybe with things like fingerprints or DNA, where your data is pretty stable. Whereas here, there's just a lot of natural variability, and this is a challenge with any kind of behavioral data. Getting population data, we have it for this study, but in general, as we'll see when we go to likelihood ratios, how do you get data to compare to build for a population of individuals? That's going to be a challenge with this type of data. And the data also must be gotten off a device. So you can sometimes get, server-side data. Say a search engine might have data from a lot of users. Some of that data is public, but we really want data on the client side, on an individual's device. And for privacy reasons, it's a lot harder to get that type of data to do research on. So these are all challenges in working with this type of data. So I'm switching gears a little bit now and getting into some of the techniques we've looked at. And the primary technique we've looked at is some of you will know about this, some of you may not. It's something called marked point processes. So point processes are a technique in probability and statistics to model events over time. And marked point processes are where we have the events have some marks with them. So in our case, think of red and blue or red and black as distinguishing different types of events on the time axis. There's a significant amount of work on this, particularly for two-dimensional spatial data. But in addition, one-dimensional and sometimes three-dimensional data. A lot of the prior work assumes that the data are stationary or homogeneous in space or time, which is not going to be the case for us. And the applications historically are things like epidemiology or forestry or astronomy, a little bit in criminology, looking at spatial patterns of where crimes occur and so forth, but not so much in areas like forensics that we're aware. So just to show you examples of where people typically use point processes and mark point process analysis, the top left plot is astronomy data. So you have spatial distribution, are they clustering, and want to answer questions like that. On the bottom, we have an example of a marked point process. This is where the red dots, I believe, okay, I don't remember what red and green are, but one of the dots is, red is either disease or pollution, and green is the other one. And you're interested here in association between the red and the green point processes. So this is now closer to what we wanted to do. We're doing it in 1 dimension. This is happening in 2 dimension. So one of the first things we did was to look at the marked point process literature to see what types of techniques people have used to assess the degree to which 2 point processes here, the red and the green, are dependent. Can we quantify that? And so I've tried to map out here the work we've been doing so far in this context. So we have a little table with 4 entries. Go back for a second. On the left side are essentially the type of scores that we're going to use. We started out using nearest neighbor matches, and I'll explain what those are in a minute. And then some newer work that we've been doing in the last definitions of those are, but we were talking about neighbors, and we'll be talking about times. And the methodology that we're using for each of these types of measurement techniques, if you like, one is population-based, where we assume we have a population to build sort of a reference distribution. And the other is newer work, is where we don't have a population or very limited knowledge of the population. We might just have 2 event streams, and we want to be able to ask a question of this. And the first sort of quadrant of this is a paper that Chris and I published this summer. So the details are in that paper. You can get to it from our web pages. So I'll go through that fairly quickly. Chris has described it. I've described it in other talks. And then I'll move on to the time-based methods, which are the newer work. Okay, so if you remember our data, this is actually real data. It's that student data where the blue times are non-Facebook browsing and the red times are Facebook browsing. And you'll remember the first 2 pairs were actually the same individual, and the third pair was a different individual. We know that. But now let's say we were just given this data and we want to ask the question for each of these pairs. How would we do that? How would we quantify the degree of association or dependence? So one method we can use for marked point processes is these nearest neighbor scores. I'll go through this fairly quickly since we've talked about it before, but we have 2 streams A and B. There's something you can compute called the mingling index. If we take k equals 1, it's just the fraction of nearest neighbors that are of a different type. So if we take we go back here and take the red dots, the red times, and we look up in the blue stream, which, on average for each red event, is it closer to a blue event or to another red event? And that will give us some information about essentially association. The other closely related coefficient that people use is something called coefficient of segregation. You can think of it essentially as a correlation coefficient. It's looking at the probability that a neighbor is of type A or B relative to if they were independent. So the product of the marginals versus conditional probabilities that you actually observe. So without spending too much time on the definitions, if you have interleaved events, for example, the red and the blue tend to happen within a session together, you'll tend to see high mingling and low segregation. And then the opposite case is where the red events tend to occur and then there's a gap in time, and the blue events occur separately. You'll have low mingling because the neighbors are, you always have the same type of neighbor, and so the fraction of different neighbors is pretty low. High segregation, just the way that coefficient is defined. So we can use these to come up with scores, and the next question is, okay, how can we calibrate these in terms of some kind of reference population? So to do that, we treat these as scores and score-based likelihood ratios. So there's going to be two hypotheses. We have our red stream and our blue stream. One hypothesis is that they are from the same source. The other hypothesis is that they're from different sources. So we'll compute a score. It could be the mingling score or the segregation score. And then we'll evaluate the probability distribution of the score under each hypothesis. And I haven't said yet where these distributions are going to come from. We're going to estimate those from the data. And then using the usual likelihood ratio, score-based likelihood ratio technique, we look at the ratio of these two density functions and get a likelihood ratio. So I'll walk through how we do that. We estimate the two density functions from population data. So with our student data, we have, order of 100 students that we can use. We know we have pairs that are the same source. We have lots of pairs that are different sources. So we can use those to generate empirical distributions of these scores. So for example, here's one for the coefficient of segregation. And I'll explain in a minute, but we're going to get two different distributions, one under each hypothesis. And then we can take perhaps a new previously unseen pair and compute its likelihood ratio under these two hypotheses. So looking at that in a little bit more detail, the likelihood ratio is just the ratio of the heights of these two densities at some point, some value for the score function. So that coefficient of segregation goes from -1 to 1. It turns out that for our data, that if there are different sources, then you tend to have a high segregation. Things are further apart in time. And if they're the same source, it tends to be lower in distribution. There is overlap. There's not perfect separation, as you might expect. Part of that is from students we have very little data for. And that brings up an potentially interesting theoretical aspect to this, is that there will be sets of events for which you cannot possibly answer these questions. They're going to be some ambiguity. One of those cases would be when you have very little data. There'd just be too much ambiguity. In other cases, when you have very dense data, it turns out it's quite hard to separate or assess dependence. If everything is very dense, things become tricky. So, the usual thing, when they cross over here, the likelihood ratio is equal to 1. So things to the right are going to have, favor one hypothesis, things to the left favor the other hypothesis. And so we can compute likelihood ratios now. So to evaluate this, just to see if this works on the data we have, we take the data. We actually took only 55 students. We ignored students that had very little data. And so we took about half the students. Remember, one stream is the Facebook request, one stream is the non-Facebook request. The way we did our experiments was we did leave pairs out cross-validation. So we take, essentially every individual has an A and a B stream. So there's 55 squared, or about 3,000 possible A-B pairs from individuals I and individuals J. I could be equal to J in some cases, that's the same source, or in most cases I is not equal to J. So for every possible out-of-sample pair, we take that pair out from some I and J individual, and then we're using the other data, the in-sample data, we estimate the probability, the density functions that we need for the likelihood ratio. And this in-sample data excludes all the data from individuals I and J, so it's constructed on completely other individuals. Although you do need to keep in mind these other individuals are all students on campus, so they're more similar than random individuals in the population. We use kernel density estimation. It's just a one-dimensional score, so that's easy. Use automated bandwidth selection, and then compute a likelihood ratio for that pair AB that we left out. So we're going to loop over that approximately 3,000 times, and from those likelihood ratios that we got, we can do things like compute receiver operating characteristics, detection statistics, precision recall, and so forth on the left out pairs, because we know the ground truth here. So this is essentially a validation experiment to see if can you detect from the data which pairs are dependent. And we found, perhaps not surprisingly, that even though the data is somewhat noisy, yes, you can do this. This is one way of looking at the results with ROC curves. The segregation index does a little bit better. It's the red curve than the black curve, which is the mingling, but they're both quite far away from if we did random discrimination. So there's certainly a lot of signal there. So that's encouraging. Now we're interested and have moved towards using the times between events, because here we're just looking at the identity of your nearest neighbor in time. The times themselves should have more information, should have some additional information. So the way we do this, just to explain what inter-event times are, let's say we have two event streams A and B like we had before, red times and blue times. I'll take one of them and I'll measure the time to the closest event in the other stream. Now closest could mean closest, previous to you in time, the previous event in B that happened before the current A event, or it could mean in either direction, could be bidirectional. If you want a causal interpretation, you think more directionally. If you don't care, you're looking offline, maybe you do it bidirectionally. I don't think it's that important, but here we do it. I have to think for a minute. I think the results here, I'd have to go back and check. I don't remember if they're directional or bidirectional in the results I'm going to show you. But the point is, I don't think it's that important for the results that we get. So you get a set of inter-event times. For every single event in, say, one of your streams, you get how far away is it from the closest event in the other stream. And you can analyze the density of these inter-event times. So for example, if one stream is a login event, and the other stream is something you do pretty quickly after you log in, we're going to see a lot of very short inter-event times. If, on the other hand, one stream is a login event for one person, and the other is some event that a different, completely independent person is doing, we should expect a much more variation in event times, much larger in inter-event times. So we can look at the densities of these inter-event times. We get entire densities, or some summary statistics. So I'm going to focus here just on the mean, which is very simple. You could use the median. You could potentially use the whole density, but that's going to be more complicated. So we'll essentially think of the mean here as like a score function that we get out of a whole set of inter-event times. So just pictorially, maybe I should have shown this slide first. Here we have blue events and red events, where the blue events are embedded within the red events. So think again of Facebook clicks embedded within non-Facebook clicks within a session. And the inter-event times will tend to be fairly small here. A different type of relationship, potentially there's dependence in this second one, but it's a different type of dependence, is where the blue events have some repulsion or sort of mutually exclusive in terms of where they occur from the red events. They're not interleaved, and the inter-event times will tend to be larger. So the inter-event times can tell us quite a lot about what's going on between the two processes without having to make necessarily parametric assumptions about how the two processes are being generated. So we could do what we did before, and it's what I'll do to start with, is do a population-based methodology, where we'll take all those students and assume we can construct same source and different source density functions. Let's see, I think I've said most of this already, so I'll skip to what it looks like. And we find, not surprisingly, this axis on the y-axis here is actually on log time in minutes. So this would be 10 minutes, this would be 1 minute down here at 0. We find that the same source, when it's the same person generating the Facebook and non-Facebook events, they're pretty close in time, not surprisingly. Although sometimes there's gaps, fairly big gaps. There is some overlap between the two densities. And then if we line up two different people and look at their Facebook events and their non-Facebook events, that's the red density, the gaps tend to be much larger, 10 minutes, an hour, or more. That's because they're just doing them independently. There are times where they line up by accident in this tail, and that's where we're going to get, we won't get perfect discrimination. We're going to have some noise. All right. So if you go ahead and do what we did before, construct likelihood ratios, using those two densities, do cross-validation, the same methodology, you end up with a very, very promising looking ROC curve. And I'm pretty sure this is wildly optimistic of what would actually happen in practice, but if you compare it to the near neighbor matches, it's perhaps not surprising that the inter-event times have a bit more information and allow you to discriminate a bit better. So I haven't given you numbers here, I'm just showing you visually. This on the right is the ROC we saw before, on the left is the inter-event times. I should say that this is work that's not yet published, not yet fully checked out. I see Chris and Hal looking at this saying, we haven't seen these slides before. So take with a grain of salt, but we might expect that the inter-event times would have a little bit more discriminatory power. which we're seeing. So I think it's very important at this point. You know, I could stop and go home and say we're done, but no, there really are some important limitations to what we've done with this. It is a single study. We've been using about 50 students in the results. That's why we really want to get other data sets here, completely different types of data if possible, different individuals. The same source Facebook and non-Facebook is a little artificial. I think it's a useful test bed, but it may be easier to discriminate. These tend to be highly embedded, and so they're probably easier to discriminate than, say, if people are using two different devices, where you have like my laptop and desktop data, which are separated in time but in a systematic way. So embedding might be an easy case. And I said that, I guess, here in the third bullet. And then the methodology requires a population of individuals to construct the denominator in the likelihood ratio. And where are you going to get that data? What's a suitable comparison population? This is, of course, not a problem only in this context for digital forensics, but in other aspects of forensics. So sort of keying off the last point, it's interesting to ask the question, if we move sort of the bottom quadrant in this table I showed earlier, where now I'm going to do something with just pair-based two event streams. And we're going to look at it inter-event times and see what we can do. Can we answer any questions if I don't have a population? I am going to cheat a little bit along the way. We do need a little bit of population information, but it's somewhat weak. It's turned out there's going to be a background rate, that time of day rate, and we're going to need to use that in our analysis. So in this part, and again, these are slides that Chris and Hal definitely haven't seen, and so I should absolve them from, if there's anybody who doesn't like these, contact me, don't contact Chris and Hal. But if we try to think a little bit more, maybe from a probabilistic statistical perspective, I'll develop a little bit of notation here. So we have a set of source times and query times. Now I apologize that when I wrote this, I switched from A, B to Q and S. So if you can do that in your head for a few minutes. So instead of, you know, A and B, I have Q and S now, but it's just two event streams. And we have the taus indicate the times of the events, and there's a different number for each one over some time span, over a day, over a week, or so forth. So, you know, let's take an example. Somebody's been sending emails to the Dean of Social Sciences here at UC Irvine, very annoying emails. The Dean of Social Sciences has kept a log of these. We have all those times. We go to Simon's computer, we see if Simon's been sending emails. We have times that Simon has sent emails, so that might be the query set. We want to know if the, you know, Simon's events and the other events are dependent in any fashion or look independent. So we're going to look at inter-event times here, and here it is directional. This notation is just saying we'll look at the time in the query stream to the closest preceding time in the other stream, the source stream. And when we start writing down this type of notation, we can start to think about, you know, the way statisticians tend to think about models for the data. So we could, for example, have a joint likelihood over both streams given some background rate. So conditioning on the background rate is going to be important, given that there are strong time of day effects and non-stationarity in the data. However, I think you know, that it's probably going to be easier to look at conditional data likelihoods. We're going to want to assess conditional independence, for example. And so what we'll look at going forward is the density of the query timestamps given the source timestamps and given the background rate. And so implicit in this is that there is some background rate again, and where we get that will be important. I'm not going to say too much about it today, but it'll be an important part going forward. So we can think of two different simple structural models for how things might be dependent on each other. We might imagine that Q and S would be generated by two different people. So there is a time of day effect. People write emails during the day when they're awake, when they're near computers, when they're not doing something else. And so you will tend to see a fairly strong, this lambda T will tend to peak, maybe in the mid-morning, and go down at lunch, and go up again in the afternoon, and decrease in the evening, and go to zero at nighttime. And so our two data streams they might share that property. They are dependent, but they're conditionally independent given lambda T. So it'll look like, and this lambda T could have pretty strong, induce some pretty strong dependence. So maybe these people are working at a company where everybody goes to lunch between 12 and 1. It's very, very strict, and they all do that. And so that might show up in both Q and S and lead to think that Q and S are dependent when in fact they're not. Or with students, there might be class effects, the times at which classes get out and so forth. So there could be all kinds of time effects in here. The other model that we might want to think about is that Q and S are being generated maybe perhaps by the same person. And so S is the sort of primary, if you like. This kind of has a causal interpretation where, you know, S is the main activity they're doing, and then occasionally they do Q. Q is dependent on some S activities. So I'll show you in a minute, but the login example, they start a session, and then during that session, they may or may not do a Q activity. So lambda is controlling S, and then Q is just dependent on whether S has happened or not. It may happen. Q is conditionally independent of lambda given S. So if we look at this in terms of equations, this conditional probability for the Q times given S and lambda, if it's conditionally independent, if it's that model on the bottom, which I guess I called, no, it's the model on the top, then Q doesn't depend on S at all. It only depends on lambda. And so we can make, here I just make some further simplifying assumptions. We could have a Markov type assumption that's often made for these types of models, where Q also each time depends, the next time only depends on the current time. We're just essentially assuming first order Markov here. If we wanted to, it's not necessary to do this. And then we could just model the differences in times, for example, with a Poisson process or something like that. These would be exponential. So again, S might be email sent by one person, and Q is email sent by a totally different person. And this model would be appropriate for something like that. The second model, where there is actual dependence, would then have that the taus in the Q stream are dependent on taus in the S stream, not on the preceding Q. And there's different ways you could parameterize this. Here, I just assume that there's no dependence on Qs on other Q times. It just depends on the most recent S time, the closest S time. And again, we could look at the difference in times and have a model of this form. So here, maybe somebody is on a computer, and that's the S times. They're doing activities in S, and then Q is when they log into a different account, but they're still on the computer. So they're going to do it in the context of using of other events. So we can use this idea then to see if, given two streams, let's come up with some summary statistic. So as before, we're going to use the mean observed inter-event time between Q and S. And we're going to have M of these. That's the number of events in Q. And what we'd like to get is assuming that they're independent under sort of the null hypothesis, what's the sampling distribution of R? Conditioned on S, we're going to take S as fixed. We've observed the first event stream. We're also going to assume we know the background rate, and we're going to fix the number of observations we have. So there should be some, even if they're independent, there should be some sampling variability that we're going to see in the mean inter-event time. And what is that under the model where S and Q only depend on lambda, and we have M events for Q. So this does require an estimate of the background rate, but I think that's just a fact of life that you'll need it, and I think it's a lot weaker than having to have actual data from a population. So you can think of situations where you would have reasonable estimates at the time of day rate at which people generally engage in, work on their computers and so forth. So one way you can get this sampling distribution is by randomization. So you just generate lots of simulated data sets. Each of them have M events, M simulated events. They're being generated by the background rate. And you then measure the simulated inter-event times relative to the fixed set of source events. And you do that K times, and you get this, each time you get a mean. In this case, we're using the mean for R. And you're going to get K values of R from the K simulation. So this tells you, if things are really independent, how much variability would we expect to see with just M events of type Q, even if things are really independent. And we can now look at the observed value for R and see how many of the simulated values were more extreme or further out in the tail. And this is effectively an empirical p-value. We shouldn't see, this should be a fairly large number if things are really independent, and should be very small if things are not independent. So what happens when we actually do this with our data? So here are two streams from the same individual. And we're essentially trying to answer the question of, could these have lined up by chance? They look like they're lined up, but could it have happened by chance? Here's the background rate that I used here. It was estimated from all the other students. This is actually pretty noisy, and in practice, you'd probably want to average over the days, which I didn't do here, so I just averaged over time. But it's essentially giving you a kind of a time of day effect for simulating the the simulated data set. So when we do the simulation, these are simulating now B streams that could have happened under the model. We get a lot of things that don't line up very well with the blue stream, but that obey the time of day characteristics. And if we compute density function for the mean inter-event times for all those simulated streams relative to the blue guy, and then look at the actual AB time. The actual AB time, the mean inter-event time is very small. We saw that before. And the simulated times have a much bigger variance, and they're much larger mean. And this is way outside. There is no simulated time that was even close to this, as small as this. So the empirical p-value here would be effectively 0 unless we did a whole bunch more simulations to get way down in the tail here. If we take two streams that are actually from different individuals, and if you look up here, it's not obvious that they overlap. The reds overlap somewhat with the blues, and this is this point I was making earlier about density, that if the blue stream is very dense, it makes the problem harder. More data here kind of makes it harder rather than easier. So it's not obvious that B is from a different individual at all, just by looking at it. We simulate Bs, and we compute the statistics, and now the event time, the actual observed, is well within what we would expect if they really are conditionally independent. It's not unusual, it's not surprising. So this is, we'd be inclined to believe that in fact they are independent here given this data. There shouldn't be any negatives down here. This is just the way the kernel density estimation was done. All right, so we can do this more systematically, and I won't go into the details of this, but basically all the p-values for the same source were essentially 0. There was almost no simulated examples outside. And occasionally for different sources, you would get a few that just by chance you couldn't tell that they looked like they might be dependent, just by chance. Those two students happen to be doing things at the same time. And that's always going to happen with this type of data. But by far, the majority of these p-values that we indicating that independence was likely. All right, so wrapping up, I think I'm running slightly over time. There's a whole bunch of things we're interested in doing, extensions to different types of events. As I said, things like cross-device data, robustness of these methods to different statistics, different metrics. I think modeling the background intensity and the sensitivity to that is an important problem. Also, another thing that we've talked about but not actually looked at is individual variability across different days. There's information there we're not using. There's theoretical questions, I think, the limits of detectability based on how many events you have and how dense they are. I mentioned earlier data sets, so I think I'll skip over that in the interest of time. One of the data sets we've been starting to look at is Reddit submissions. This is a public data set where Reddit has released all of its posting data, including the timestamps. If you don't know what Reddit is, ask somebody under 21. They should be able to tell you. But it's a big online community, essentially, with lots of subreddits. And so what we're looking at here are the different subreddits, different types of actions as people post and move from subreddit to subreddit. And there's a lot of data, so this might be a good source. Here's some of the data. And one of the problems here may be that the density is too high. Another issue here is that for users that post a lot, in fact, some of them are bots, automated bots, and not real people. It turns out in this data, in these examples, the first two are the same person, just going to different subreddits, and the bottom one is two different people. This is future work. We're starting to look at this. We also have spatial data with another project that we've been doing that's funded by NSF, where we have GPS locations. We can even get that down to the level of, so about 2% of tweets have GPS turned on. And if you localize down around the university here, we see that where the students live, and when the students are on campus, they're tweeting a lot, but where the faculty live, there's very little tweeting going on. All right. And another thing that I think is quite interesting that I didn't say much about is the patterns of event dependence. And we'd like to understand this a little better. So essentially, the first two up here are embedded. where maybe the embedding, when that second type of event, those Facebook events, they're just interleaved. The person is doing some Facebook, going back to their other stuff, or they're switching, but it's still embedded within that session. So that would be the red is embedded within the blue sessions here. A different type of dependence is where you have exclusivity or sort of mutual exclusion, where, you know, after I finish one type of activity, I do a second type of activity. Perhaps not always, but if it happens, it's going to happen after the first type of activity. So I do one session, and then I go and do some phone calls. So that's, you know, might require different types of models and so forth. You can have completely repulsive activity. This happens in spatial statistics a lot, where you have one type of tree, another type of tree, and they spread out so they don't get too close. And, you know, again, if it's dense or sparse, this makes a difference. So there's some interesting questions there. All right, to summarize, you know, analyzing digital evidence in a forensics context is increasingly important. It's just going to get more and more important. So it's a very useful area for CSAFE to be looking at. Up to now, statistical methodologies have not been playing much of a role in this. User-generated data, I think, potentially has some interesting aspects that could be amenable to statistical analysis. And our CSAFE work has shown that there's promise. But I think there's a lot more work to be done, both on the theory, well, in theory, experiments, and in making these techniques practical for actual digital forensics practitioners. I will stop. Thank you.
So do we have questions? From anywhere. Guess no questions.
Alicia, there's a question here in Irvine from Simon Cole.
Oh, go for it.
Same source, different source. What's the forensic application of those problems versus other kinds of digital forensics?
Yeah, so Simon asked, why did we focus on same source, different source, as opposed to other types of problems we could have looked at in digital forensics? Is that, or what is the practical application of same source? What kinds of problems? So at the Minnesota meeting recently, for example, at Chris's poster, a group from the Netherlands came up and gave us an example of different phones that people are using, burner phones and their own phones. And so you have an event stream of one phone, an event stream of another phone. You would be interested in asking the question, can I relate the two event streams? Do they appear to have, in that situation, you might expect this mutual exclusion type of property, and how likely is it you would see that by chance? So in talking to some of the people at NIST and reading some of the literature, it seemed like this was a problem that occurs in practice, where there's maybe two different accounts being used, computer accounts, and you want to assess, is it the same person behind both accounts or not? I think let me answer the question slightly more honestly and say that there's a disconnect a little bit between what we're doing and the practice of forensics. This is one of the few problems we were able to find in the first year where we could actually get our hands on using some modeling techniques and so forth. But it may be a little bit of a chicken and egg. If we show you can do useful things with this type of data, people may find broader uses for it and applications. Lots of hand waving going on here in Irvine in case you can't see me. So. Back to you, Alicia. Or anybody else who has a question?
Other questions? I actually have a question myself.
Sure, fire away.
So you were looking at two different types of events. Can you look at more than two types of events?
In principle, yes. There shouldn't be any problem with doing that. It would just, I think, complicate the notation, the methodology. You'd have to figure out what specific question you're asking. It could be that you have, four types of events. Let me think for a minute. You might be asking, are any pair of them dependent, for example, out of the four? So there's a little bit of combinatorics there. That could be one question. There is work in machine learning where they take system-generated data, like a lot of machine-generated data, and try to infer dependence across maybe thousands of event streams. That's probably not of interest here, but I think, in fact, it makes sense that the real data that you get, that I talked about at the beginning, coming off a device, will have, browsing events, search events, phone calls, emails. So it's a very good question, Alicia. I without, again, hand-waving here, I'm pretty sure the methodology can be extended to math without too much difficulty. And partly we don't focus on that because we don't have data at the moment that reflects that. But I think the methods could be extended to that.
Thank you. Anybody else? Questions? If not, thank you very much, Padhraic, and thank you everybody that's listening online. We'll announce our next webinar sometime soon, hopefully. Bye-bye, everybody.